When I was asked to do a talk here, I sent 3 different possible tutorials that I prepared for a summer school last summer. And 2 of them were quite entertaining and lots of pictures and that sort of thing. And one of them was really dull and boring. He picked the dull and boring one. So you're going to have to suffer. Anyway, before we get started with that stuff, this is actually, Peter and I made the remark about how close she could get to the rocket. Well, we were a lot closer to the rocket. This was the day before ACE was launched into space from Vandenberg, carried up to 45,000 feet underneath an L-1011, and then released. And there's this terrible 10 seconds while the rocket is falling, and you're waiting to see whether it actually turns on and goes. But it did, and it went into a perfect circular orbit at 650 kilometers. And there's another difference in this picture, too, which is, of course, I don't look any older now, so... There we go. So I'm going to talk a little bit about the first steps of learning how to do the mathematics, like the numerology, the hands-on stuff, to be able to actually write your own code and extract information out of remote sensing data. So I'm going to go through and talk about a simple spectrometer and some of the elements of an instrument that you have to consider when you're doing it. Talk something about instrument characterization, so that you know how to take the numbers that come out of the instrument and turn it into physical quantities applying to the atmosphere. And talk about some of the steps forward to bring you up to the exhaustive standards of some of the other talks that we've had over the last couple of days, doing really advanced fitting techniques that are not so difficult as you think to actually put into code and to make run. And if I have some time at the end, I'm going to share some lessons learned in the business of putting instruments into space. And it's kind of amusing and kind of depressing at the same time. Well, everybody does their own picture. In the process of preparing specifications for the putative polar highly elliptical orbit science component of the proposed Canadian polar communication and weather satellite, we were looking at what wavelength ranges we would design into the instrument. And so I made a plot that was limited to the range of wavelengths that we were considering. And you can see all of the molecules that have been discussed in the past few days. And the thing that, of course, stands out is that, like fingerprints, each of these molecules has a lot of distinct information, sometimes large cross-sections, very obvious high impact here, some of them very tiny and requiring great care to extract them from the spectra you take in the atmosphere. The instrument that I'm going to describe so that you have a physical picture in your mind of what we would use to make the measurement is actually the optics of the sun photospectrometer that we flew on the shuttle, and essentially the same optical layout as the Maestro instrument flying on the ACE satellite. It uses an EG&G Reticon detector, which is the same detector that was used in GOM and GOM 2. It's about 1 inch long, 2.5 centimeters long, and about 1/10 of that in length. So it has about 100 to 1 ratio in the size of the pixels. It's really designed to go into a spectrometer. There are about 1,000 of them along that distance, so they're all very close together. So it produces the ability to make a fairly high resolution spectrum with a modest dispersion. Okay, basically the instrument is one component and one detector. It's a concave holographic grating. It makes an image of the entrance slit at the exit position, and of course it's dispersed along the length of the detector, so we actually can make a spectrum in one integration cycle. They were really designed for very high sensitivity, And so that means you would integrate maybe for many seconds and then quickly read the detector out to get the whole spectrum. In the case of Maestro, though, we have to make a measurement in a third of a second if we're going to be able to manage a 1 kilometer vertical resolution in occultation mode, because that's the rate the satellite makes the sun rise and set through the atmosphere. So we were forced to let it look directly at very bright lights and to make very, very short integration times. And there's a lot of interesting detail about how to actually do that. The way the detector works is it has actually photodiodes inside, and you connect up an electrometer to the video line, and the electrometer recharges the photodiode capacitance when you select the gate and gate it onto the video line. So basically you charge up all of them to the same common potential and then isolate all the diodes and let light fall on them. And the electron hole pairs created by the arriving photons or thermal generation will gradually discharge the junction. And then when you recharge the diode, you measure how many electrons it takes to put back on. Each photodiode can store up to 62 million electrons, and your electronics has to be sensitive enough to recharge that. One of the sort of theoretically interesting things is that there are not actually any separating barriers in between the pixels. It's just where the location of the electrodes are determines the collection area of the pixel. And so if the light shines directly in the middle of the pixel, all of the charge will accumulate on that one pixel. But if the light lands in between the two pixels, it'll get shared between the two pixels. So right away you know that you've got an aliasing problem you have to deal with. You've got to at least co-add across 2 pixels, and you must make your entrance slit image at least 2 pixels wide. And that was the design goal for Maestro, to make the entrance slit just 2 pixels wide to minimize that effect. Because if we add the 2 pixels together, we'll get the same signal that we would have had on a single pixel. Okay. And of course, at the end, the electrometer voltage that's generated by integrating up the charge is read in to the computer. Spectra are co-added and coded and sent off to the spacecraft bus. As I mentioned in the stray light talk the other day, it is one of the technical issues that we have to deal with in understanding the quality of the instrument and in terms of being able to make corrections to that kind of thing. And so I just want that to be in the back of your mind, that we need to separate out the different impacts that can occur from different characteristics of the instrument and be able to understand how to model that in the retrieval model so that we separate out instrument effects from the actual atmospheric effects that we're trying to model. That's another instrument, same kind of thing. One of the things that always puzzled me when I first saw Beer's law is, why is the missing light proportional to the amount of light and come out as a log function rather than just the absorber absorbs so much light? It's very simple, because each molecule has a certain affinity for photons called the cross-section, centimeters squared, and the light coming in is so many photons per square centimeter, so you multiply them together, and that tells you the probability that you're going to absorb a photon. So necessarily the delta I, the missing amount of I, must be proportional to both the density of molecules, the strength of the molecule, and also the brightness of the light. So that's why we wind up with a logarithmic function as the determination of the optical depth. Now, now I'm going to get into a little more mathematics and try to work our way up to an optimal estimation, or to the stage where optimal estimation is just the next step. Just to be on the same page, you'll find in some cases I dropped the summation symbol with the implied double summation there, or double subscript indicating summation. One of the simple things that we need to know about for later on is covariance. Well, if we have a sample of data xi, if we have many ni data points, and each of them are multidimensional, so in this case you could think of the I being the number of spectra and the j being the number of wavelengths, then we can actually calculate the mean for the j by summing up over all the i's and dividing by the number of i's we had. And the same thing is true for the xk. And so if we run through all the possible j's and k's, we'll get the sigma for the individual j's on the diagonal of sigma jk, and we'll get the correlation coefficients on the or the covariance coefficients on the off diagonals. Now, if we're actually making a measurement with an instrument, the instrument collects information about the spectrum, but it doesn't actually give us the whole spectrum. The spectrum is continuous. It has an infinite number of wavelengths. The instrument has a finite number of detectors, so we have to relate the spectrum to the actual measurement the detector makes. So in our model, we would model at high resolution compared to the instrument, and then apply a correction to make the instrument model agree with the physical instrument. And in this case, I've written it as capital S here, the slit function. When we integrate overall wavelengths and include the contribution from each different wavelength weighted by the slit function, we get the signal that the instrument would actually see. Okay? In actual fact, of course, this is a mathematical concept. The instrument really is seeing the effects of light, not the light itself. And so we have to know something about the responsivity of the instrument and how it responds at each wavelength. Now, both of these are already simplifications, because who says that the slit function has to be the same at every wavelength? And who says that the responsivity of the pixel to all different wavelengths is necessarily the same? So I've already divided up some of the terms here in the way that we normally assume. But it is an assumption, and you have to go back and test the instrument and make sure that the assumption is close enough to the reality that the answers that you derive by using that model are going to be physically realistic. So if we go a little farther along, well, we know that the extraterrestrial flux, the flux from the sun, or the unabsorbed source radiation, is going to be attenuated at every wavelength by whatever optical depth is in the path between the source and the detector. And we can also show very easily that the sum of all the different kinds of absorbers that can go on can be used as a total measure of optical depth. That's because you can write out the equation in this way and show that the product of all of the individual absorption, the individual transmissions, is the term determined by the sum of all the optical effects. I use the C to refer to the constituents, the gases in the atmosphere, R for the Rayleigh scattering in the atmosphere, and A for the aerosol effects. So in the case of the gaseous absorbers, well, each one of them will provide its own little contribution to the total optical depth. So we can write down the gaseous total optical depth in terms of the cross-section of the molecule and the surface density of the molecule. So I use an eta in here so it would appear a little more general, because later on we'll see that there are some other effects that we can easily include in the forward model and be able to generate retrieval steps for. And so using eta here, in this case it's representing the column density in molecules per square centimeter, essentially the product of the concentration times the distance you're traveling through that concentration, and integrated up over the whole path light between the source and the detector. And if we just take that term and plug it into the equation we started with here for the intensity. So we've got the extraterrestrial intensity, or the unabsorbed intensity, the source, attenuated by all the molecular absorptions. We're doing a sum over the J's for each of the different gases, ozone, NO2, CHO, whatever. And of course then it's weighted by the slit function to finally produce the signal that would arrive at the detector. I'm ignoring, or at least assuming, that the responsivity of the detector is the same at all wavelengths, so that we don't have to deal with that at the same time. So one approach to fitting is to actually minimize what I call the square error, the difference between the modeled, little m there, the modeled intensity and the actual observed intensity. And to minimize that, if we just make a little change here to make it look a little easier, we've got the log of the model intensity and the log of the observed intensity squared and summed over all wavelengths. And that depends, of course, on the amount of each of the absorbers that we wrote into the equation on the previous slide. And if we go to minimize that, it's quite easy. You just differentiate with respect to each of the things in the model that you can change, and get an equation that looks like this. Well, if we start off with some initial guess of what might be in the path between the measurement and the light source, then we'll have some value that's probably close to the observed number, but obviously not going to be exact. So we want to actually try and use the equation to search for a better fit, which would allow us to say, well, if the model agrees well with the observations, then the elements within the physical model must be in agreement with what's in the atmosphere. A lot of assumptions in all this, you know. Well, if at one point in time we've produced a guess at the model value, then we could write this little delta L as the residual error. And that turns the equation into this form, replacing the difference with the delta L. Now, if we're not actually at the minimum, which we're seeking, in other words, adjusting with respect to each of the parameters in the model and getting as close to a minimum as we can, and I've drawn a little picture here for two elements in the sum, eta 0 and eta 1. One can imagine that there's a curve that represents the minimum in each direction, and if we are trying to find the global minimum, where you're at the bottom for each of the n parameters that you're trying to retrieve, then we could say, well, let's take a little step from where we were and hopefully get a little closer to a better solution. So a little step away in many dimensions, represented by the k, will be the differential with respect to each of those directions times a little increment in each of those directions. So if we want to get a better answer, then we would adjust the sum by a little change and hopefully move in a direction that would bring us closer to 0. So if we expand that equation out, you'll notice that the differential term here and the one there are really the same vector. It's just the differential with respect to each of the components of the model. So if we write that out, it looks like this. So we're summing over all of the wavelengths still, and we can recognize that these are really matrix forms. So we can replace the double product here of all of the differentials in the form of a two-dimensional matrix, and the other term in terms of a product of a vector and two vectors rather. So the final equation that we have up here, written in vector form, looks like this, and we can recognize that we can get a solution by just inverting that term and calculating the delta eta. Now, if we calculate delta eta correctly, then we can go back and say, okay, let's make a correction to eta that is used in the forward model, and then run through this again until we've approached the minimum. The reason it's not a solution in one step is because we're expecting that the model may be somewhat nonlinear, and you'll have to take another couple of steps so that the differentials you calculate are exactly right at the point where you find the minimum. Now, in terms of real data, I thought I'd just show you a few pictures of the data that we're collecting with the Maestro instrument on ACE. One of the goals in the design was to be able to handle a very large intensity range. So you need to be able to look directly at the sun when it's above the atmosphere, and then you need to still be able to make measurements when the light has gone down by orders of magnitude by traveling through the atmosphere and being absorbed. So when we're looking directly at the sun, we're being bombarded with photons, and the integration time is so short that you don't have time to read the detector out. So we actually read 1 pixel at a time and reset the detector in between until we've accumulated a whole 1,000 pixels. But as the light gets dimmer and we're seeing a lower level of photons, then we start by binning 8 pixels at a time and resetting in between. And as it gets dimmer, we go to 16 and 32 and 64 and so on as the light gets dimmer and dimmer. So that's why all of the data seem all crammed together here at the top. Our goal is to try and get the photon wells as full of photons as we can. But of course, it doesn't look much like a spectrum. And now down here, of course, this is getting down to dark count, where we integrated the entire detector and then read out all of the pixels in a hurry. So the first step is to convert to counts per second to account for the different integration time that's represented by each of the different pixels here. Some of these are co-added, some of them are just single groups of 8. But and as you go from spectrum to spectrum, the integration times are changing all the time. So the first thing we did was reconstruct the individual spectra by dividing by the integration time. And this is the picture we get. These are 2 separate instruments, the UV part shown in the blue and the Vis near IR part shown in the red. And so what I've done is actually shifted the scale on the axis. The length of the axis is the same on both sides, but this one's been shifted to account for the fact that the absolute sensitivity of the 2 instruments at a given wavelength is slightly different. And it shifted so that the top spectrum right here will line up. And you can see from the fact that all of these other spectra going all the way down orders of magnitude all line up still, that the whole system is extremely linear over a very large range of intensities. And that's another thing that you have to test your instrument for. If you just assume your instrument's linear, you may get some really bad surprises. So in the end, if we take a bunch of spectra taken when the light is not traveling through the atmosphere at all, we can generate a solar reference spectrum, which is this red one. And you can see that based on the standard deviation of the 20 spectra that we put together, that the standard deviation of the mean here gives us an extremely precise reference at almost the entire spectral range. Now you'll notice that there are some little features in here. Some of these are solar Fraunhofer lines, or well, essentially Fraunhofer lines, cadmium D line and so on. But there's also this Edellining effect, and it's due to the fact that there's an overcoat on the detector of silicon dioxide that's 2 microns thick. And so as the light comes in at different angles from the grating, there's an interference pattern generated. And you can actually write a simple program and pretty well match up that behavior from the dispersion of the instrument. So now we have a nice spectrum we can divide into the individual spectra taken throughout the occultation. And that makes a picture that looks like this. And now we don't have to do any shifting of anything because we've normalized out the individual count rates, the absolute sensitivity of the instrument. Again, you can see that the optical depths at the point where the 2 spectra come together agree very well. And you'll notice the scale That's about 150, a factor of 150 in attenuation there, which is quite a huge amount. And we're still getting good optical depth measurements down there at the bottom. Okay, back to the math. One of the things that is interesting is the question of how you actually proceed to generate the terms you need to do that solution that I just showed. In other words, how do we calculate the differentials? Most people's first instinct is to say, okay, well, we've written a forward model, we'll perturb the forward model and subtract the two answers and then use that as an estimate of the discrete differential. But if you do a little more work on the pencil and paper side before you start writing the program, you can do a much better job of it, and I'll explain why. Remember, this is the equation we started with, and it looks pretty frightening in terms of taking a logarithm of it. How are we going to proceed to find differentials analytically? Well, it turns out not to be that difficult. If you remember, the differential of the logarithm of something is just dx over x, and we can do the same thing. We can differentiate this term and then divide it by that term. And that's exactly what I've shown down here. So here's the 1 over I, the calculated model spectrum, and then we start to differentiate. Well, an integral is really just a sum of terms, so we just go inside and take the appropriate differential of the term that contains the independent variable that we're differentiating with respect to, and then add up the answers. The reason for doing that is because if you compare the analytic derivative to the discrete derivative, there's quite a difference. This is fine in principle, where in your head you can imagine these numbers are all exactly and perfectly known to an infinite number of decimal points. But when you put something into the computer and do the calculation, well, if the delta x is too small, you won't make any change in the least significant bit, and you'll get 0 for an answer. Or maybe you'll change 1 or 2 bits, and it won't be really the right answer. So if you make delta x too small, then this thing is just going to be all noise, because you're dividing a tiny number by another tiny number, and you'll have trouble getting the right answer. The analytic approach avoids that. And the other thing is that it means you only need to do one pass through the model, because you've already differentiated and you've got a model of the differential elements as well as a model for the forward model of the spectrum. And I'll show that here on this page. Okay, so here we have the term that I just showed before, where we're differentiating this thing. Having done the differential, we wind up with the cross-section weighting these terms, and that's something that we can calculate with a simple forward calculation and get the answer for each individual derivative that we need. Let's say there's 20 constituents. We don't have to run the model 21 times. We just have to run it once. And it's even better than that, because a lot of the terms that are in the forward model equation here are exactly the same terms that are in the forward calculation for the differential. So this makes a really big increase in speed in terms of calculating the Jacobian elements. Now, in practice in the computer, we don't actually have to use an infinite number of wavelengths. We just have to use enough wavelengths that we represent the behavior of the instrument properly. In general, you'll need to have 5 or 10 times the number of elements than the minimum sampling rate of the instrument. So you want to have a number of points across the slit function, so you describe it well. And it's particularly the case for ozone, because the ozone spectrum is so steep, and the intensity spectrum is even steeper than that. So you need to have a pretty good representation of the true spectrum before you weight it with the finite weighting function that represents the slit function of the instrument. Now, when you look at this thing, it's hard to believe that it was actually possible to build something like a Dobson where you just apply the slit function just to the cross-section. But in actual fact, if the cross-sections change slowly with wavelength, or the source function changes slowly with wavelength. In fact, waiting for an effective coefficient actually works. That's what this really is. It's really the effective cross-section. But that is the element that goes in the Jacobian matrix, as you saw before, in order to be able to do an inversion and calculate the answer. So the important part here is that the only difference between the kernel of this integral and that one is just the product, or making a product with the cross-section for each individual absorber in turn to produce the n different differential elements that make up the columns in the Jacobian matrix. Now, we didn't talk about noise at all, but different parts of the spectrum have different noise. If you go into the UV, the light gets dimmer and dimmer and dimmer. You have fewer photons, so the square root of n is the number of photons you collect, so the noise is going to increase. You don't have as many photons, you're going to have a noisier measurement. So it becomes advantageous to actually build a noise weighting into the system so that, as David was mentioning earlier, we can actually see a graceful behavior and not a sudden behavior in the performance of the thing. The shorter wavelengths that become nearly zero, their influence just disappears because the noise estimate matrix will make that go away. And in fact, this is called chi-squared. If we have a sigma matrix and we weight by sigma minus 1, then this is actually a chi-squared minimization. And so in a practical scheme, you'd actually minimize chi-squared rather than just minimizing the square error. Sometimes it makes very little difference, but at least this is the correct way to do it. That also has an additional advantage, because if the sigma that you put in here is actually representative of the distribution of the individual measurements that you're making, then each of the degrees of freedom will contribute a value of 1 to chi-squared. And so if you were doing, let's say, 10 constituents, then you'd expect chi-squared to have a value of 10 if the data set that you have, the model that you have, and the noise estimate that you have are all in agreement. And so by knowing what the size of chi-squared is, you can have an idea of how well you've actually represented the observation you're making. And it has another advantage as well, which is if you are trying to have, this is one constraint, right? It's essentially a minimization constraint between your model and your observations. But if you have insufficient information for that to actually extract all of the results that you should be able to extract from it, then you can find an easy way here to put in an auxiliary constraint. If you have in your auxiliary constraint, you also can write in the form of a chi-squared minimization, something multiplied by the covariance matrix inverse. Then you know that it's of order unity as well. So you can just add these terms together and minimize them as a unit. And this is, in fact, a way of describing the Tomyu-Tikhonov and the Rogers optimal estimation as well, where the auxiliary constraint element, the extra chi-squared element that you put in, is simply defined by the product of the difference from the a priori data multiplied by a covariance matrix inverse that represents the statistics of the distribution that you're trying to find. And that's often determined by climatology. And of course, even though you've decided to have a term that you minimize related to the difference from the a priori, and you also have a term to minimize to fit the spectrum, you can also just impose a smoothing function as well on top of that by adding in a third term. And in fact, that just simplifies to enhancing the covariance matrix that you derived independently with some cross-correlation between rows. So it's very easy to generate these auxiliary constraints. And by having used the inverse covariance matrix to scale to order unity, you can just sum together the terms and then do a global optimization. And the equation that pops out is exactly the Rogers equation. So one thing it does for you in looking at it from this point of view, from the numerical side, is to realize that if your error distribution isn't exactly Gaussian, but the distribution you based your a priori statistics on is representative of the distribution of observations you're actually going to make, then the method is still going to work, because the basic mathematics tells us that you're going to get a chi-squared value that's of order unity as long as those two distributions are well described by the covariance matrices. There's a couple of other little tricks too. In the beginning, when people were doing DOAS, they would do some kind of retrieval for the constituents like this, and then they'd do an outer loop where they tweak the wavelength a little bit, and then they do an inner adjustment, and then they tweak the wavelength a little bit and try to get the spectrum to agree better, taking into account possible small shifts or stretches in the wavelength dispersion equation. And in fact, you don't have to do that. All the pieces are laying around to do it analytically again. The definition of a shift and a stretch is basically generating a new wavelength based on your original assumed dispersion equation, and then adding a little shift. And a stretch, of course, is just making it get bigger as you move away from the center, right? So you can define the stretch in terms of a center wavelength subtracted from the old wavelength, multiplied by a constant, and adding the shift. And in order to do the differential that we need to put into the Jacobian, all we have to do is calculate what is d lambda by d shift. And that's pretty easy in this case. D lambda by d shift is just 1, right? So we do d lambda by d shift and then di by d lambda, and from the chain rule. The same thing down here, di by d stretch, di by d lambda times differentiate with respect to stretch, and that's the only term left. So you can even go on and do this to higher and higher orders, squared, cubed, whatever you need to do. If you're covering a very large number of pixels with a system that may have a little bit of thermal problem or something that causes some curvature in the dispersion equation, you can actually plug those all into your Jacobian along with the constituents and do one single retrieval. The only caveat on that is the one thing I didn't mention that complicates things a little bit more is if you simply go and use the equations as I outlined them here, you can have a problem, because these things can be 5 orders of magnitude different in size, and your matrix will be badly conditioned, and numerically it'll blow up and it won't give you a good solution. But the fix for that is simply to operate and do your retrieval in terms of d log eta instead of just di by d eta. And that just simply means multiplying this thing by the cross-section. It's quite easy to just write those equations down and turn that out. So again, you may choose to use a fractional approach here to ensure that all of the rows in the matrix are of the same order and you don't have numerical effects giving you the wrong answer. I have a kind of a fun story about this one. I wound up refereeing a paper written by Susan Solomon and Richard McKenzie, and it was looking at DOAS and trying to improve fits. And everyone knew that gases like NO2 and ozone had temperature dependencies, and they were seeing residuals that had something like the differential of the cross-section or in the artifact. So the problem was, well, how do we handle the fact that we don't know what temperature the gas is at? Well, Richard McKenzie's approach was to actually fit 2 different cross-sections and get two different amounts of the absorber, Susan had a slightly different approach, and I can't remember exactly what she was doing. But I wound up refereeing this thing, and I've got these two different things. We're trying to measure the amount of ozone, right? We're not trying to measure the amount of blue ozone and yellow ozone, or ozone at two different temperatures or something. We're trying to measure the amount of ozone. And the physics has got to be simple enough that these two different approaches could be understood. And I thought about it for a day or two, and finally realized that if you actually start thinking about the true amount of the absorber, that the equations come out pretty easy. If you pick a reference temperature, then the cross-section at some other temperature can be represented as a locally linear expression like this. So if we have a value for d sigma d temperature, we multiply it by the difference from the reference temperature, and that's the little correction we need to get sigma at some other temperature. Okay? So if we just plug that whole thing into the Beer's law expression, it's pretty easy to see that it just wanders right through. We wind up with one term in terms of the cross-section and the amount of absorber, and another term in terms of the d sigma dt multiplied by the temperature difference in the amount of absorber. Okay? So if you've written a program to do the retrievals, which I had done, it was pretty easy to recognize that this is a cross-section, and this is a cross-section-like thing, right? So your program could just have this as one cross-section, this one as another cross-section, and the thing that you'd be retrieving here is the product of the temperature difference and the amount. So once you've done the solution and you've got the true amount of absorber, and you've got the amount of absorber times the delta T, you can divide that into here and get the delta T. So you get both the temperature and the absorber by this very simple adjustment to the retrieval scheme. Well, in conclusion, I'm not really going to quit right yet, but this is an important conclusion. Any instrument you make is going to respond to a lot of different things. And your job as an experimentalist is to look very seriously at how to build a model of how that instrument will perform and come up with a series of tests that isolate the individual effects and allow you to deal with them somehow. Some of them you can deal with on a design basis. In other words, you build the instrument, it has a thermal problem, you figure out where it is, you put in thermal compensation, then things are okay. Or you calibrate it so that you can do a correction, whatever. But you have to do a lot of testing so that you can identify all of these different elements and then deal with them properly in your forward model, or the physical model you use to retrieve your atmospheric values will not give you the right answer. Now, I was going to, this is kind of mandatory these days. When people are funding you, you have to tell the world that they've been funding you. But there's something else on this page that I'd like to point out. I'd like to disabuse you of Peter Nell's notion that there's no Canadian Space Agency. There is a Canadian Space Agency, and they actually fund my chair at York. In fact, they put up about half the money. And not only that, there are also instruments in space that are making measurements of the atmosphere that are Canadian. OSIRIS on the Odin satellite, the Swedish satellite, is from the University of Saskatchewan, and it's been running now for, I think, 11 or 12 years, and still working very well. And we also have a Canadian satellite that was built in cooperation with NASA. They provided the launch, and it has two instruments. One is a Fourier transform spectrometer, and the other one I'm the PI for, the Maestro instrument, measurements of aerosol extinction in the stratosphere and troposphere retrieved by occultation. It's one of the few honest acronyms floating around. And those two instruments are on the Canadian SciSat satellite making occultation measurements, as I was describing. And it's now in its 11th year. It passed 10 years in August. And that's the end of the main part. But I've got a few other things if you have a little bit of time. I've actually only gone about 7 minutes over, and I started 10 minutes late, so that's not too bad. If you're still awake enough, I think this is kind of fun. These are lessons learned in the process of building instruments with companies, putting two instruments on the space shuttle, and putting Maestro on ACE. Don't build computers. Buy one. We built one for a shuttle flight in 1992 because we wanted to meet the RF requirements laid down by NASA, not really realizing that they wrote a waiver for every single computer they ever flew because you couldn't get it quiet enough. And we almost made it. We were less than a factor of 2 over the limit. But it was a waste of time. And it blew up on orbit because the astronaut decided that he didn't like the fact the batteries were going flat and connected it up to an auxiliary power unit and then left it on. And it was on too long, and a regulator blew out, and we lost the computer. So you don't want to do that. And the corollary of that is don't use the batteries. When we were partway through the flight, they were asking for permission to plug the thing in. And we had to go into mission control, with 100 people there all looking at a huge screen and stand and pull our forelock and explain to the mission manager why we wanted to plug it in. And he said, "Don't you know that batteries don't work up there?" Everybody knows batteries don't work up there. That was the second time we did that. And it's something people don't really realize, that batteries work by having a chemical reaction go on beside the electrodes. And you have to get rid of the ions that have done their job and get new ones to have the battery continue to work. And guess what it is that drives the circulation? Density, gravity, right? Simple, very simple. But a lot of instruments never did what they were supposed to do on orbit. Yeah, every instrument needs someone to look after it. If nobody's really intensely interested, things just kind of come apart. That's why they have principal investigators for instruments, so that there's somebody that's on the hot seat that's actually going to make sure. And if you start managing a project, you got to make sure that it gets the support it needs, or it will, again, just drift into nowhere and never finish. And making hardware to go into space is quite difficult. So if you can write paper and borrow somebody else's computer, that's a lot cheaper and a lot better. Matrix management is a disaster because the guy that's responsible for part of your project doesn't report to you. Your problem isn't his problem. He's got other people that have given him problems, and if yours is a minor problem, your priority goes to 0 and your project doesn't get finished. And the same thing is true. If you're running it, you need to have some control over it. And if you're responsible for somebody else, try to remove obstacles, not generate more. And that's really important because an individual can only do so much work, right? And this is an important one. There's always corporate knowledge in a project at a given stage. And if you try to change things without thoroughly analyzing it again from the new perspective, you're liable to wind up with a hidden problem that comes out later on that the original guy might have understood. Yeah, and you do have to have schedules, but you don't necessarily meet all the deadlines. But if you don't have some ability to control the path, you'll never finish. And this is from a different standpoint. Jim Drummond is famous for running around saying, "Test as you fly." And it's absolutely important. We didn't fully do that with ACE because they wouldn't let us. The engineers said it would be too expensive. We had to test the two instruments and characterize them on a separate platform and then put them back together. And it led to the fact that we really didn't know how to get the data down when it was on orbit. It took us quite a little time to rewrite software in order to be able to decode the data because we never tested sending the data all the way through the system and out the other end. And in the end, building space hardware is a unique thing. Engineering is the art of never again making a mistake you already made. Putting something into space is getting it to work the first time. Think of your car. Cars are really reliable, right? And that's because they've been building cars for 100 years, right? But They still do recalls on new cars, right? And they don't have near the problem you have putting something in space. There you go.
Okay, thank you. Do you have any questions?
Everybody's in too big a hurry to go somewhere else. 감사합니다.
Okay, I think I should have to leave a little early.